have seen that the earth was formed by accretion of planetesimals, and the formation of the earth is very closely related to that of the solar system and the sun itself. What we will do now, we will look into the composition and the mode of formation of mantle and crust. Crust is the outermost portion of the earth on which most of the organisms, including ourselves, survive. Mantle lies below it. From the study of earthquake waves propagating through deep inside the earth, and by analogy with the composition and structure of meteorites, we now know that earth has a layered structure. This layered structure is shown in the diagram. If we look at the diagram, we see the crust extends from the surface of the earth to a depth of average 40 kilometers. From there starts the mantle, which extends from 40 kilometers to a depth of 2891 kilometers, and below that depth up to the core of the earth at an average depth of about 6371 kilometers is the core. We will concentrate on the models of formation of mantle, and then we will quickly take a look into the composition of the crust, making certain hints at what could be the possible mechanism of formation of the crust. The crust, regarding its formation process, poses a problem, because unlike the mantle and definitely unlike the core, the crust is much more heterogeneous with a very stark difference in composition and structure between the crust that underlies the continent, we call them continental crust, and the crust that underlies the ocean, which is oceanic. Before going into the details of the crust, let us take up the mantle first. We know, and it has been proven with the help of meteorites and other planets, that at one point in the history of the earth, and that is pretty early in the history of the earth, because of a giant impact, certain portion of the earth got molten, forming what is now called a magma ocean. That ocean used to extend all over the earth and continued at a depth of up to 1000 kilometers. From this magma ocean, because of higher density, iron and those elements that have a strong affinity for iron got separated because of the pull of gravity. They settled to the bottom of the magma ocean, and further they moved down in the form of pillar like things called diameters to the center, forming the core. Thereby, the differentiation in this magma ocean led to a partitioning of iron rich core and the overlying mantle. This is the process by which the mantle is formed. We will look into the details of the composition, especially the elemental abundances of the mantle, to understand in more detail how it evolved through time. In the previous part of the section, we have seen that origin of the mantle is associated with origin of the core. Now, mantle is such a huge area, to be precise, such a huge volume, that it is almost impossible to sample it. It seems rather ridiculous to say that, because there is a cover of crust average 40 kilometer thick that hides the mantle from our direct observation. So, whatever little we know about mantle is from study of the earthquake waves, how their velocities change within it, and comparison with extraterrestrial objects, that is the meteorites, and we have certain access to directly observe the rocks brought from the mantle, brought from the depth of the mantle to the surface in two different situations. When a magma, which is a silicate melt generated usually at the depth of the earth by melting of the magma, rises to the surface of the earth. On its upward journey, it can pick up a few unmolten fragments of mantle, we call them xenoliths, and bring them to the surface. The question is, how do we know that these are not the part of the magma but mantle? A first order observation is that there is a big difference in the color of the rock that is holding them as xenolith and those fragments. The magma melt crystallizes to form a rock called basalt, which gives you usually black color in the sample, whereas those fragments believed to be of mantle, called mantle xenoliths, are deep green in color. We find that these mantle xenoliths are composed of predominantly two minerals, olivine and pyroxene, both being silicates of the element magnesium with a smaller content of iron. The density of these samples as measured in the laboratory matches that of the density of the mantle measured by seismic wave velocities. So, by analogy with the meteorites, we have seen that the mantle is expected to be made up of magnesium, silicon and oxygen as the dominant constituent with a small fraction of maybe iron. Our very limited but very important direct observations of the samples from the mantle supports that. So, the general conclusion is that mantle is dominantly a zone containing mostly magnesium silicate in two different mineral forms called olivine and pyroxene. These two minerals, though compositionally very similar, differ in their atomic structure. That is why they are classified as two different entities, two different minerals. In addition to the mantle xenoliths, there are portions on the surface of the earth where not just small fragments of mantle, but an entire section of mantle with overlying crust are emplaced on continents. These portions of mantle and the crust originally belong to oceans, that is the crust underlying the oceanic water. By processes that we call tectonic processes, the rocks from this depth are brought to the surface, which needs at least about 4 to 5 kilometers of vertical transportation. This amount of vertical transportation is calculated with the help of the average depth of the ocean, which ranges between 4 to 6 kilometers. These sections shows association of upper mantle and then the entire section of the oceanic crust. These associations are called ophiolites, and they are formed in zones of tectonism where two portions of the earth usually move towards each other and converge, forming a very important plate tectonic scenario of subduction zones. Tectonism refers to very large scale movement on the upper portions of the earth, including the crust and upper part of the mantle, due to the action of large stresses. It is believed that whatever feature we see on the face of the earth is actually contributed to by plate tectonic processes. Now we know that the broad composition of the mantle is magnesium silicates. When we look into the greater details of this composition, we will try to evaluate what are the other components that are present in the mantle and how do they compare with the composition of the meteorites, that in turn refers to the composition of the solar nebula. To do this, we will be using a few graphs. This is a plot of two variables in the two axes of the graph. The vertical axis, that is the ordinate. Along the ordinate, that is the y axis, the ratio of weight percentage of magnesium over silica ratio and along the abscissa, that is the x axis, the ratio of weight percentage of aluminum and silica for the mantle rock samples and different classes of meteorites are shown. If you look at the upper central part of the graph, we will see the composition of the sun's photosphere. The bright envelope around the sun is also plotted. The plots from the mantle shown in green with peridotites written can be joined by a straight line, and this straight line shows a negative slope. That means the higher values of mg over SI ratio gradually becomes lower towards the right. This trend of the peridotite compositions is the result of extraction of a magma of basaltic composition. As the basalt magma takes out more of iron than magnesium and aluminium, the residue, that is the mantle peridotite, becomes enriched in magnesium. In this plot, if you look to the upper part, we will see some green dots. Those are the peridotites from which the maximum amount of iron is extracted. As a result, the proportion of magnesium increased by the highest amount. The increase in silicon due to the extraction of the basalt is balanced out due to normalization of both axes by silicon. The trend of the plot of peridotites, that is not a single point but a series of points along the line on the top central part, shows that within the present day mantle there is a variation in the composition, indicating the mantle is heterogeneous in composition. Just to refresh our memories, basalt is a volcanic rock formed from magmas erupted on the surface of the earth and is essentially formed of pyroxene, which is a magnesium iron silicate, and a plagioclase, which is a feldspar containing calcium, sodium, aluminum, and is also a silicate. The bulk silicate earth, represented by the pink ellipse at the central upper part of the diagram and mentioned as BSE, represents the range of estimates of composition of the primitive mantle as estimated on the basis of meteorites and the composition of the photosphere of the sun. When you compare the plots of these two ratios for peridotites shown as green dots with that of the composition of the meteorites shown as blue triangles, we see a contrasting pattern. The plots of the meteorite, when joined by a straight line, shows a positive slope of the line, which is described as a positive trend. Both mg over Si and Al over Si ratios increase together from E chondrites through HL chondrites and reaches a very high value in carbonaceous chondrites. There are 4 different types of carbonaceous chondrites shown in the diagram: Ci, Cm, Co and Cv. All of them has the same character, that they have higher Mg over Si and Al over Si ratio than the other meteorites. It is interesting to note, if this trend marked by the blue triangles are extended, shown as the blue straight line, upward, it intersects the broken green line showing the trend of the peridotites at a point which falls nicely within the elliptical zone marked as the BAC, bulk silicate earth. The argument seems acceptable that the best possible composition as shown in this diagram of the bulk silicate earth will be the zone where the trends of concentration of these two elements in the meteorite intersects the trend of peridotites. It is noted, however, that for certain elements whose concentration is calculated for the mantle does not match the concentration shown by the bulk silicate earth. We will try to look at these discrepancies in the following diagram and try to find out what could be the reason for it. If you look at this diagram, we see in the y axis the variable is mantle normalized to magnesium and chondrites, which means the concentration of an element is divided by the concentration of Mg in that sample from mantle, that is the peridotite, and this ratio is again divided by the concentration of the corresponding element in the chondrite meteorites. Similarly, the plots around the x axis is actually the names of the elements whose concentrations are plotted along y. If we look at the diagram, we see there are three colors used. The one green to the extreme left is marked refractory, the one in blue is marked moderately volatile, and the one in pink to the extreme right is marked with volatile. Among the refractory elements, we find there is a big drop in the concentration of tungsten in the mantle compared to that in the chondrites. But for the concentration of hafnium, uranium, aluminum and also calcium, it is very similar to that in the BAC, the bulk silicate art or the meteorite. This is a very curious observation because tungsten is low. When you go to the blue curve, we see a slightly lower value for silicon, but extremely low value for gold, copper and sodium. So again, this clearly shows a deviation in the concentration of the Earth's mantle from the model of bulk silicate Earth, which refers to the original composition of the solar system. We also find the elements marked as volatile in the pink shows a very, very low concentration within the mantle compared to the chondrite. Of these elements, zinc and rubidium stands out in their low concentration. The question is asked, what could be the reason for this variation, this deviation from the concentration of certain elements from that of the carbonaceous chondrite meteorite, because there is reason to believe, and we have seen that all these things came out of the solar nebula, that is the carbonaceous chondrite and the Earth and its mantle. One explanation for the depletion of certain elements, especially the volatile elements plotted to the left of the diagram, is that they are being more volatile. The Earth has lost them in the pretty early phase of formation when the Earth was hot. Tungsten and aluminum has almost equal condensation temperature. That means to vaporize they need almost similar temperature. In spite of the similarity of their condensation temperature, the concentration of tungsten found to be very low compared to that of the aluminum. The abundance of aluminum is comparable to that in the carbonaceous chondrite, whereas the abundance of tungsten is very low. This is a perplexing problem, but when we look into the composition of the core and when we study a property that is of some elements having affinity to some other elements, tungsten has an affinity for iron. Therefore, tungsten will stay in the company of iron. Core is a huge repository of iron. Therefore, during the early part of the differentiation, that is the formation of the core, tungsten went into the core along with iron. This has reduced the concentration of tungsten in the mantle. So we see there are twofold explanation for the depletion of certain elements in the mantle peridotite. If the material is highly volatile, then these elements will be depleted in the mantle. Also, if there are certain elements in the mantle which have affinity towards iron, they will sink to the core, thereby lowering their concentration in the mantle. The next diagram shows the details of the siderophile affinity of certain elements and how their concentration in the mantle is controlled by the degree of their affinity towards iron. This diagram shows the abundance of the siderophile elements in the mantle once again normalized with respect to the magnesium in the corresponding mantle samples and the concentration of corresponding elements in the CI meteorites. When you look into the diagram, we see the most siderophile elements are plotted to the right and the least siderophile elements are plotted to the left, and there is a distinct segregation in their abundances with respect to that in the chondrite. We see the most siderophile elements have the lowest abundance in mantle peridotites, and the least siderophile elements, though low in concentration but still very close to the concentration that found in the carbonaceous chondrite. So, we have two factors that are controlling the abundances of the elements in the mantle when compared to that of the chondritic meteorites or the bulk silicate earth. The volatile elements are lost, therefore, their concentration drops in the mantle. Also, the siderophile element, because of their affinity, sank to the bottom in the core and lowered the concentration of those elements in the mantle. The crust poses the most complex problem regarding its average composition. The crust has two components, continental crust and oceanic crust. Their elevation above the mean sea level are different. The average elevation of the continental crust is less than 1 kilometer above the mean sea level, whereas the elevation of the mean oceanic crust is between 4 to 6 kilometer underneath the mean sea level. This difference in elevation possibly reflects the difference in their composition and structure. Whatever we will be discussing in this part on crust is mainly based on direct observation of the crustal rock samples and also study of earthquake waves that pass through the crust. There is a first order difference in the composition between the continental crust and oceanic crust, in that oceanic crust, as is known from the samples and seismic velocities, is dominated by the rock called basalt, which is again dominated by iron, magnesium and silicon, whereas the continental crust have an average composition close to that of a type of granitic rocks, which are dominated by plagioclase, which is made up of calcium, sodium, aluminum, silicon and quartz, that is silicon dioxide. Not only there is a first order difference in the composition between these two, there is a difference, much too complicated difference between the structure of these two types of crust. From seismic velocities, it has been shown at a shallower depth the continental crust is extremely complex with numerous layers having numerous configurations and showing different velocities. Compared to that, the oceanic crusts are much simple, having a layered structure. This relates to the fact that the continental crust and the oceanic crust possibly has two different types of origin. As we understand today, from the very similarity in the composition of the component of oceanic crust basalt to that of the melt derived from the mantle, the oceanic crust is formed by crystallization of magma derived from direct melting of the mantle. Interestingly, however, the composition of the continental crust, which is very close to granodioritic or dioritic, a rock intermediate in composition, the continental crust, which is made up of average granodiorite or diorite, the rocks composed of almost equal amount of silicon, aluminum, oxygen, magnesium, iron, sodium and potassium, there is a first order difference in the composition of the oceanic crust and the continental crust. Oceanic crust is dominated by iron, magnesium bearing minerals and mostly constituted of a rock called basalt, whereas the continental crust is dominated by silicon, sodium, potassium, some extent calcium, having a very low density. Chemical studies shows that the basaltic crust can be and is in a perfect chemical equilibrium with the mantle underneath. That is, it can be derived directly from the crystallization of a magma which has formed due to the melting of the mantle. Interestingly, however, the average composition of the continental crust, as mentioned earlier, that forms mostly a rock called granodiorite, is completely out of equilibrium with the mantle immediately underneath it. This has a very important implication. While a melt can be derived directly from the mantle and it can be crystallized to form the basalt forming the oceanic crust, the formation of continental crust is much too complex. Because the composition of the continental crust is out of equilibrium with the average composition of the mantle, there must be some intermediate steps that changes the basaltic melt derived from the mantle into that of a granite. These steps are very difficult to understand, and still a lot of research has been done on it. Thus we see the continents on which we live, though very nice to us, but poses a very complex problem regarding its origin. If we summarize what we have discussed in this session, a contrast between the processes of formation of mantle and crust become apparent. Mantle has formed very early, related to the very early differentiation of the earth that has separated the core from the earth. So it is a very primary product of earth formation. However, the crust is a product of selective melting of mantle. Crust is not there when the earth was first formed. The selective melting of the mantle has created the crust. The magma that came out from the mantle directly crystallized to form the oceanic crust. But the situation is much too complex for the formation of the continental crust. It is now believed from the study of the chemistry and geochemistry that continental crusts form at a very important plate tectonic scenario called subduction zone, where the basaltic melt are generated, they come close to the surface, but then they undergo very complex kind of chemical processes, as a result of which there are 2 or 3 intermediate steps has to be crossed to reach the composition of that of the continental crust, which is rich in silica and poor in iron and magnesium. So the mantle is very old, the crust is also old, but crust is constantly getting renewed in the ocean. But once formed, the continental crust, because of its low density, is very difficult to destroy. So we have crusts which are as old as 4.6 billion years old. That means almost very close to the process of formation of the earth. But this formation of crust was not by direct derivation from the mantle. It proves that there are much more complex processes of chemical differentiation was operative even in the early part of the formation of earth.